welcome to the second session. The first session was basic science. Now we have a lot of fun applications of digital fabrication. Once you can connect data to things and things to data, we'll be looking at the things you can do with it. So remotely, we're fortunate to have Dave Arnold talk about food. Then Eric and Europe will talk about prototyping machines. Sally, we're fortunate to have talk about big things. And Chris will end with flying things. For the remote speakers, about 15 minutes talking, 5 minutes questioning, and there is remote translation, so speak slowly for the translation. And so with that, I'm delighted to have Dave Arnold joining us from New York. And let me ask you to start by introducing yourself. And I'll give you a
Sure. My name is Dave Arnold. I'm the Director of Culinary Technology at the French Culinary Institute in New York City. Thanks for having me. I wish I could be there in person. I hear Lima is one of the great food cities in the world, and I've never been, which is a shame. It's a travesty. But my job is to think about new techniques, technologies for chefs. So I was approached a number of years ago by the team at Cornell, the Fab at Home team at Cornell, and they said, hey, would you like to have a 3D printer and see whether you can get any good applications with a 3D printer for food? And I'm never one to turn down equipment of any type. And so I said, yes, please, bring me a 3D printer.
Sorry, Dave. Dave,
yeah?
Your presentation is not yet projecting. I'm going to pause just for a minute until we figure out why.
Well, I mean, the first image, and I can talk for a while, is just an image of the machine anyway. And, they've probably seen a similar image. So, I mean, I can keep talking while you work if it's okay with you. It doesn't bother me any.
Please proceed. Thank you.
Okay. So basically, the idea is people want this technology, 3D printing, to reach a wider audience. And if you can get a good application for something like food, something that everybody likes, something that everybody is interested in, then maybe those applications can help propel the interest in the technology as a whole. And the Fab at Home crew at Cornell is one of the crews that's making affordable units that you can either manufacture yourself or buy a kit. For relatively, they're in the $2,000, slightly under range for a piece of equipment. Now, the way the Fab at Home works is it's basically it's a version of fused deposition modeling. So what it's doing is it's taking a syringe and extruding out material in a line and then moving a carriage down and then incrementally doing that and building up models, right, one layer at a time. Now, they use syringes, they can have other tools, but basically the idea is they're going additive, and it's the medium that you're printing has to come out of the tip of something. So it has to be, one, pumpable, and two, homogeneous, right? So those are the main problems that I'm dealing with. And when you're working with basically what that means is a paste, right? So classic things that this machine can print well are icing, right? Molten chocolate, silicone rubber, and anything that is that you can squirt out of a syringe. Now, that's a huge challenge because for me, my job isn't just to make kind of an interesting shape out of something. And my job is to try and figure out an application that's going to work for a chef in a kitchen, or what I like to call the real kind of killer application of this technology. Now, there is a market now for this kind of technology. Let's say you had a pastry business and you were making cakes, and your cousin comes in and wants their face in a cake. Very simple. Take a couple of shots. Do a 3D, with a camera. Do a 3D, model on the fly. Technology's already there for that. Put it into the machine, and it'll print in icing Billy's face on the top of the cupcake. This is a valid business model, and it's very interesting. And I think it could sell a lot of units to individual people, but it's not the kind of game-changing food idea that I really wanted to deal with. So, when they first came with the machine, they're like, well, let's make something. Is the presentation up yet or no? I can see it's not up yet, so I'll keep talking. It doesn't matter. So basically, they said, well, what do you want to print with it? And I didn't really have much to think about, so I just took scallops, and I blended them with a product called transglutaminase, which is an enzyme that, it's going to be hard to translate, transglutaminase, an enzyme that binds proteins together, and we extruded a shape out of the scallop paste, and we set it and we fried it. So we ended up with, and you'll see the picture eventually, a space shuttle made out of scallop paste, or the Great Pyramid of Giza made out of scallop paste. Now, this is the inherent kind of situation, and a problem is, to me, from a restaurant standpoint and from a food standpoint, it's not an interesting problem to say I'm going to take a bunch of different homogeneous pastes and form them into various shapes. It's not the same situation as when you're doing fabrication for a prototype and you need to get a shape out to prototype out a new idea, or you need to get a shape out to actually build something functional. It's food that you're going to pop into your mouth right away. And if I was going to do it in a restaurant, if I was going to make this, right, I wouldn't need one of them, or two, or 10. I'd need hundreds, sometimes thousands, depending on how you're doing. So right away, I knew I had a problem.
I apologize for the delay. We have your presentation. Guide us through what you want us to show.
Nice. Well, you can just go to the second. I'm only on the second slide. There you have, let's see, there's the machine still, and let's see, space shuttle out of scallops. It's a little old at this point because it's been sitting on the plate for a while, but you get the idea. But fundamentally, if I wanted to make a space shuttle out of scallop paste, what I would do as a cook is I would make a mold, and I would just have a bunch of silicone molds, and then I would just strike scallop paste, boop, 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 boop. I'd make hundreds, in sheets, mold them out, and they would be done. Because, and rapid prototyping would be a great way to make that mold, right? And that's an extremely valid, use of rapid prototyping technology. But that's not what I'm talking about today. I'm not talking about using rapid prototyping to help the cook do something else, like make a mold. Or like another thing, I think with the way powder printing technology is going now, in the near future there's going to be chefs, I hope to be one of them, who are printing their own plateware out of something like plaster and a powder, infusing it in a vacuum with vitreous slip and firing it to get finished plates, that you can produce relatively quickly. Great application of rapid prototyping, but not really what I'm talking about here. I'm more interested in how can we use this to make interesting and good foods, new foods, something that's worthwhile doing, something I can't already just do with my hand by cooking, or isn't better done with some other technology. Okay, so the fundamental problems, and by the way, there's different problems with printing technology. Some are current technical problems, like resolution. When you give someone something on a plate at a restaurant, or if you're going to make a football player out of chocolate and put it on the top of the cake, the resolution has to be high enough such that your customer is like, wow, that looks like my favorite football player, and that's really cool, and I'm going to pay for either the unit to make those cupcakes at the party, or two, pay for the cake that someone else is going to fabricate, right? But the resolution is just a technical issue that is going to be solved, in the near future. It's more a fundamental issue of what is the application for taking something that is homogeneous, like an icing or chocolate, and forming it into a shape. And where's the interesting stuff in the food space for that? And for me, it's not making shapes. That's not what I'm interested in. I'm interested in a new food. So I'm going back to the idea then that I'm not interested in using it just to make one-off cakes. is there a way we can use rapid prototyping, and specifically the machine that I have, the Fab at Home, which is, basically, like I said, position model. Is there a way to use this machine to make something new that you couldn't make any other way, and to use it actually as a prototyping machine, as a way ideas for something you produce in mass quantities later. So if we can go to the next slide. An interesting thing to play with that this machine lets you play with is texture. So Jeffrey Lipton at Cornell, we had to do a video for CNN Money, talking about how much I loved rapid prototyping in food, and I was like, Jeffrey, I haven't really come up with an application that I really love, that I really think is a game changer. And I was flipping through his book, looking for, his book of pictures, looking for something that really caught me, something I thought was really interesting. And do you have up there? Yeah, so if you can play that video, this is a technique he uses called stochastic printing. And stochastic just means somewhat random. There's no sound, so I can talk over it while it's playing. And basically, the idea is that instead of printing a very accurate picture of what of the model, right, we print a very rough picture of the model, and we actually hold the tip of the syringe above where the model is, and you get this kind of squiggle down printing. And by adjusting the parameters of the print, you can adjust the texture of what you're getting. So now this is something I find is very, very interesting, because now we're using the technology to create a whole new texture, right, that's not available before. And so then I had to think, well, what kind of material is going to be really good? What material is there that's a food that is incredibly delicious, right, that is a paste that can be extruded through a syringe that I like, that might have a good application for this technology, right? And the answer was, next slide please, masa. So masa is, and this is one I ground at home using an old school metate mano, right? Masa is corn that's been treated with alkali, that you then, after you treat it with alkali, you grind it, but the alkali treatment does a couple of things. It's cool because it's the entire corn. The germ is there, the broken down skin on the outside of the corn is there. It's fantastic, but it has some amazing properties. The same properties that make it great for tortillas, right? That it sticks to itself extremely well, that it's extremely moldable, and two, that it does not adhere to other things very well, right? Means that it's fantastic for printing. Fantastic. It's like the stuff is made for printing. And it satisfies my criteria of it is incredibly delicious. It's a traditional product. It's easy to make, right? You wouldn't typically, when I do it, I make it from corn from scratch, but if you're just working in the lab, you buy masa flour, maseca flour, and you can make the tortillas with it. And I was like, okay, so look, I have a material now that I think is valid to use in the machine, valid from a culinary standpoint. It's going to produce something delicious. We have a technology, stochastic printing, that is, I think, going to allow us to do new textures, and then we roll with it. So the next slide, please. If you see it, this is something we printed, and you can see that the look of this printed stuff is kind of Velcro-y, right? And you saw kind of how it printed, how it squiggled. If you go to the next slide, please. This is the whole procedure that you would basically print out. Then we steam the masa to cook it, but maintaining the shape of it. So we steam it without agitating it at all, and then we deep fry it. And what you end up with is this crispy, crunchy, awesome, really incredibly delicious product. And if you go to the next slide, please, you can see the internal structure of the material can be varied. Even in the inside of the material, you can go from dense to, just look at the last slide, so you can see how undense we can go, how we can really vary the texture. And then if you could go back one, it'd be great. But you can see that we can vary the texture from the inside to the outside. We can vary it on the fly by changing the parameters, and we can do it in a way that's very inexpensive, right? If I was going to make this for a living, what I would do, and I think Jeffrey Lipton at Cornell has already filed some sort of something in case we go to Frito-Lay and talk to him about it. I don't really I'm not really interested in business or patents or how that works, but you would never mass produce this item using this technology. You're using this technology the way it was originally intended, as a prototyping tool, as an extremely valuable prototyping tool. So we can sit there and we can adjust textures, we can adjust line thickness, we can adjust height of the item, we can adjust all of these parameters in a very quick, very intuitive way, and then, later on down the line, yes, we would hire someone and they would build, a 1,000 nozzle plate that was extruding mass amounts of masa at a time onto a conveyor that would then go through a conveyor steamer and then through a conveyor fryer and go into bags as snack chips, right? And so this is the kind of technology that really this is the use of the technology that really gets me interested, because now we have something that you weren't able to create before, and that just hand printing wouldn't be a substitute for, and molding wouldn't be a substitute for. And we're interested in using this not just with masa, but perhaps making really interesting, very porous, light meatloaves that would then act like sponges and absorb sauce. These are interesting applications to me. I think what we need to get away from is the idea that this is just going to be something that is used to make a shape. Or the other thing I really think we need to get away from, and this is what a lot of people, when they first think of 3D printing, they think of the Jetsons. And what they want, or what they think they want, is that in 100 years' time, you're going to walk up to a machine and you're going to press a button, and all of a sudden, the food is going to be presented to you. And as a cook, to me, that's kind of horrifying. It's a horrifying prospect that you would remove the cook from the equation, or that you would remove the idea that or that you would encourage the idea that all of your foods be reduced to a paste and squeezed out of a tube in order to create some sort of ersatz meal is incredibly horrifying. And that's why, to me, it's coming up with these new techniques, I think, is how we're going to push forward the idea of this stuff as a prototyping tool. Now, and I know that pretty soon we're going to have to stop to do questions, but one of the places where 3D printing is going in the food world is printing of meat. There's a lot of people who are interested in meat analogs and meat substitutes and new kind of meat technologies. The current state of the art of printing tissues is mainly based on what's called a scaffold printing. So what they'll do is they'll print a porous scaffold shape of collagen, which is basically a connective tissue, and then allow cells to grow on that to produce tissue. Now, again, to me, there's something horrifying about this, because what you're doing, it's great. Like if you're a vegetarian and you really, really want to eat meat, then I guess this is a good idea. But for me, meat, and this is the problem with all meat substitutes, is meat isn't just an overcooked, chewy block of something to be infused with the flavor of whatever the sauce is. To me, meat is an animal that has been hopefully treated well, hopefully slaughtered properly, that had a good diet, and that you care about the way the muscles are and the way the marbling is, the taste. To me, meat is important and should be treated as such. So the idea that you would print the meat is crazy. And I've said this many times, and then, but I'll end with this, you never know where technology is going to take you. A couple of weeks ago, I had someone from the corporation called Organovo, who, without scaffolding, prints actual human blood vessels, starts with undifferentiated cells and prints whole blood vessels without using a scaffold. And they claim that in 10 years' time, they will be able to produce an actual marbled cut of meat that has never been from a killed animal. Now, I'm skeptical. I'm skeptical that it will happen, but I'm eagerly awaiting that kind of technology. Because to me, it's all about the taste. Does it taste good? Does it taste as good as the product I started with? Are you doing something that is worthwhile? Are you pushing forward, or are you merely using the technology as a gimmick? And so that's in a nutshell kind of what I think about with food and 3D printing.
Wonderful. Questions for a working chef about rapid prototyping with food? First question is, when does the cookbook come out? No, sorry.
Well,
sorry.
you know,
I'm going to rephrase the question: is when did the design files come out?
Right. Jeffrey Lipton, I think, has them. Anyone who has a machine like this, I don't think I printed the recipe, but I'll call him for the. He has the printing, like the printing protocols. And I'd be happy to post those and get those up. And I'm sure Jeffrey would be happy to do it too. And I'd love to see people playing with this as a textural idea. So I'm going to do that as soon as I can, hopefully next week.
Great. Any other foodie questions?
I'm interested if others have commented on how much the printed masa resembles a block of ramen.
It was just the observation that the printed masa looks a bit like a ramen block.
Sure, and if you think about the way that ramen is made, right? They're extruded, kind of. I believe that's how they're made. Extruded in a line, wavy, cooked, fried, and then put out. So there's a lot of similarities, right? But the way that ramen was designed is let's industrialize noodle production. So that was where that's where that started. On this, even though visually there's some similarities. From a textural standpoint, when you put it in your mouth, it's it doesn't taste like chewing on, and not just because it's made out of masa, but it doesn't taste like you're chewing on a block of ramen. We get to play with the texture in a way here in a rapid prototyping environment, in a way that you wouldn't get to if you were starting with the big machine on an industrial line. Does that make sense?
Yep. And in fact, can you comment on the diner reaction in the restaurant? Talk about how people react to this sort of food.
Oh, well, we never put it into the restaurant we have at the school is the students do the cooking, right? So we don't get to do too much of that, but everyone who had them was like, wow, this is great. I want bags and bags of them. You know what I mean? And that in essence is the problem, because you eat the first one and you're like, wow, I want another. And you're like, you gotta wait. We're printing. You know what I mean? And so it's like really, it would be hard. There are certain restaurants that could do it that don't have a lot of covers. The covers means a lot of people they serve in one night, and they could conceivably have the machine run all day and print out enough for like a pre-meal snack for somebody. But it's really more about just getting the parameters right and then going and scaling it up.
That's great. That's a great intro to not engineers doing stupid printer tricks with food, but actually a chef thinking about food. So, thank you.
Hey, thank you.
Okay, thank you, Dave. Now
Thanks a lot.
We're going to switch to it and transitioning from Dave to the next presentation. Fab at Home actually was born at Fab 3 in South Africa when Hod Lipson came to talk about the research and saw the need for accessible tools that led to the great work that Hod and Evan and Max and all did on it that led to this. Microphone doesn't exist. They're having trouble with it. There's then been this very interesting evolution through the history of 3D printers that's led to one of the nodal points is Ultimaker that you've seen today. So we have Joris speaking locally and Eric joining us from the Netherlands to talk about Ultimaker.
Did I first set up the screen? My name is Joris van Tubergen. I'm from the Netherlands in Fab Lab Utrecht Protospace, and I'm proudly to present the team from the Ultimaker. On the screen is Erik de Bruin. He's in headquarters Ultimaker.
Hi.
And I think somewhere over there is also Martijn Elsman, another part of the Ultimaker team. And I give the word now to Erik.
Okay, thanks a lot. First of all, let me say it's an honor to be able to speak, remotely though, but thanks a lot. Okay, let's start with the movie, I guess.
One moment.
Kijken. Dus. All right. So I'm going to talk a little bit about the journey that we've undertaken, and which was a really exciting and also interesting journey for us. So that's one part I'm going to share with you, what we've been doing. And also, of course, I'm going to tell you a little bit about the machine itself, which is also very nice because you can actually see the machine, the actual thing, right in front of you, printing. So that's thanks to Joris, who was demonstrating the machine during the event. So, okay, let's carry on to the next slide. I'll be waiting to show you that I'll have to, I'd like to see the next slide. So as the left part, I'll talk about the mission, the thing we're trying to achieve here, and also because we're doing it as a business, the way we are trying to do this, and also the challenges that we are facing and how we address them. So to start with, let's talk a little bit about us, not too much, but we've actually started with this project by meeting in a Fab Lab, and it actually all started with the RepRap project. And what we wanted to do is build a machine, and the emphasis really was on the machine itself at that point, because it was a real challenge already to just build the machine itself. So I'd like to, if we go to the next slide, tell you about why Ultimaker actually exists today. So to a large extent, it is due to the RepRap addiction that we all have. We really like understanding and seeing how this machine worked and how we could get it running. But that was really something that took a lot of effort and a lot of time. So when actually the time we were building on these machines, when the workshop that we were doing ended, we wanted to carry on with this. So we were so addicted that we had to invent something new to be able to continue this. So, well, meeting in a Fab Lab was critical to the actual, to making this possible to develop this machine. I'll show you one of my co-developers and colleague as well. This is Martijn. Hi. So, and to summarize, a lot of the things, a lot of the elements that were responsible for the Ultimaker are actually present in a Fab Lab. You have access to knowledge, you have access to people who can teach you things, and you can share the excitement, so more people will know about it, and then other people who are interested in joining can find you. So all in all, it's a very functional model to start something new from a Fab Lab. And that's what we did. So you can go to the next slide. And I'd like to tell you more about the machine itself. Because the machine was actually, to some extent, born out of excitement, but also some level of dissatisfaction about the limitations of the printers at that time. So what we were doing, you can go to the next slide. We were working on the RepRap project at first, and one of the problems there was that we were building machines, but every machine was different in many, many ways. So the parts we were using were slightly different. All of the settings and measurements were slightly different, which made it very hard to just print. So that's why the emphasis was on the machine. And it was hard to operate, and the machines were quite heavy, and at many points we had to walk long distances with heavy machines. And of course that's good exercise, but we really wanted to have a lighter machine. So, and also printing took a long time. If you had to print even a tiny object, it would really mean that you have to wait for a very, very long time. And in general, the printer was not for everybody. We were very excited about it, and we were interested in knowing about how it worked, but we knew that not everybody needs to know about microcontroller programming to be able to use this, and we wanted more people to be able to use this. So what we were thinking of, what would be the ultimate 3D printer? Well, we were thinking that it would need to have consistent results. That means that if it works once, it should work the second time. If one person can assemble it, then the other person should also be able to assemble the same machine and get the same result and get it running. So getting everything in a box and just use the IKEA hex key to just put everything together, that should be very easy, and there should not be many more tools to get it running. So, and it should be, of course, be very easy to operate and a stable production machine, so that you could print one day and you can keep printing for more than a year at least. So it has to be small, but still be able to print large prints. That's probably one of the important properties if you have a small place to stay and you want to be able to keep your machine in one room, then you need to have a small machine. But still you would like to print bigger stuff. So a lot of these things actually came together when Martijn made his first design of what you can see on the outside, the frame of the machine. And then we got really excited, and we were generating lots of ideas about how to do this. So next slide, please. So we also made this extra large version, the tall version, and you could actually print almost human-sized bodies, so or other parts, of course. So it was really fun to make variations, but also to get this really in a state that it would work very well for people that assemble it. It has to be easy to assemble. And also, of course, speed was an important factor. So for speed, what we did, please go to the next slide.
Sorry, Eric, 5 minutes left for you and yours and questions, so we'll have to go a little faster.
Okay, yes, I will. Okay, so one way to increase the speed of the machine is to simply lower the mass, and then you can control it faster and still have a very accurate print. Well, for assembly, we designed it in a way, next slide please, that you, sorry, there's one hex tool missing, an image of that. So we designed it so you the hex key mostly. And so we could carry on to the mission, episode 3, next slide. So an important part of the challenges that we had as designers, but also as a business, to make sure that we have a consistent flow of parts, so that all of the batches of products that we send out would actually work very well. And it's a real challenge, but it sometimes it requires you to just throw out some parts. And in a way that's a real shame, but it's the only way to really get it working well for everyone. So one of the things that wasn't completely foolproof is the extruder, which is why we have to assemble it for you. So we try to design most of the things so that it's foolproof, and if we can't do that, we will have to assemble it ourselves, which is a lot of work sometimes. Another challenge is making sure that if we can build it, that somebody else can also build it, and this requires a lot of knowledge transfer. So we have to understand what somebody who is building it needs to know. And sometimes it's hard because as a designer, it all makes sense that you've done it in some way, and then you see somebody else building it, and you think, wow, that's a completely different way. And that's also possible, but it's not what we were thinking of. So actually, we are learning how to talk about the machine by seeing people work with the machine. So actually, we are learning even more than the users might be learning. And there's an important step that we took before we actually launched it as a product that could also be bought by people via the website. We gave several workshops where people could just build a machine with us and we could see what they were doing. And if something wasn't completely designed in a way that it was foolproof, we actually went back to the drawing board and redesigned it because we could see what went wrong. And just after a while, we were able to say, well, I think it was a good moment to start selling it to people who we can only communicate with via online.
Eric, we're up
So,
to the time. Eric, we're up to the time for questions,
okay.
so we need to let Joris get in and then get to questions.
Of course. I'll try to go even faster. So next slide, please. And then the next. So to wrap it up, we went from a machine that was very hard to construct to a machine that could actually just print. Next one. So you can print pretty stuff in much detail. And the really fun and amazing part was that the people who had these machines were showing us what you could do with it, because you can do so much more than we were initially thinking of. And some of the users, next slide, were actually improving the machine in a way that well, we could think of, but they managed to actually pull it off. So it's very nice to see that you're not in this alone if you share the information and if you allow other people to do very interesting stuff.
Just a small movie demonstration for the speed.
So this is because of the low mass, you can accelerate it pretty fast.
It can travel up to 500 millimeters a second if you tune your machine fine. So, and people really print in that speed as well.
And one of the very interesting users of this machine as well is Joris, who is a great example, and we should probably talk about what he's been doing himself now.
The good fun about this machine, it's so easy to set up that even me as a designer, I'm not a technical guy, I even can make this machine. I think a lot of people seen this machine building. It was in pieces when we brought it. We started building it Tuesday 4 o'clock, and at Wednesday morning we made the first print. So it's really easy to build, and it makes it for people like me also possible to tinker it a little bit, to make it faster or to make it better. And maybe I don't like more quality, I like make bigger products. So that's for me important. And the previous slide you saw, these were jewelry designers. They're also not technical people. They build the machine and they put in this plastic, they give it away, and other people cast it in directly in gold. So you don't need to print the wax, you can also print in ABS or PLA. It's nice to tinker that way. Another nice project is Janine. She's disabled. She built her own Ultimaker, or at least with a little help from other people. And now she's able to print her own hands to pick up some candy. And she's actually really using the printer for her own products, for her own needs, because she cannot buy it, or somebody else can make it, but it takes a long time. And now she's able to make it herself.
We're out of time and I want to get to questions.
Yeah. One of the good things about the workshops is that if you build them together, you're already a community. So if you want to build one, you can better find 5 more people together, because then you have this local community. If you have more local communities, then you can get to the online community and you can help each other. So if you get stuck, then it's better to do. And I think this is the second last one. And then this is the last one. Thank you.
Questions about Ultimaker for Joris and Eric? Right.
The price.
And how do you buy it?
You can buy it on the ultimaker.com website, and it's a machine. It costs €1,400 including tax. It's also open source. You can download the drawings for the laser cut files on Thingiverse. Software is open source, and yeah, it's maybe a little bit more expensive than a MakerBot. It's a different machine. It's easier to set up. I think the design looks better. Martijn, who is sitting in headquarters, Ultimaker, he's, I think, one of the first non-technical people involved with building a technical machine, and that makes a huge difference, that you get a designer involved in a product, and then you probably get maybe a more user-friendly product as well. And by getting more designers involved into a machine, you get also nicer products, better products, and less technical products.
Can you talk about low-end 3D printers have made low-end objects? They make ugly things. Your surface finish is great. The build quality is really nice. Talk about
Actually, this resolution is really bad.
But talk about the optimizations you've done for just the general build quality.
Optimizations I have done for typically this phase.
You're producing really nice things.
Yeah. I typically make the machine actually less precise to print faster, so I put in more material to build faster. But it's really nice to make. This cup, I started it in the beginning of the presentation. I can pour some water in it after the presentation, so you really believe it's a real cup. I went out to print it. I could print it in 20 minutes, and Martijn was so eager to make the same cup with the high resolution nozzle, also in 20 minutes. He's able to print it in 20 minutes as well, but in better quality than I do. That makes I can change back to the original nozzle, but I think if he can print it with the high quality nozzle in 20 minutes, I should be able to print it in 10 minutes. So there's always a nice kind of competition, making things faster or better.
Okay, all right, last question.
Is there any limits on the geometry?
Limits on geometry. How do you handle things like nested parts or overhang?
A nested part and overhangs, it's not typically this machine. It's part of the technique. If you use FDM techniques, you always have the problem with overhangs and support material. It's possible to make a second nozzle on it for commercial machines do as well, and print support material. I think it's more a role of a designer to get used to the tool you have. If you have a laser cutter, you know the limitations of the laser cutter because everybody's used to it. If you have this machine, it's too new. So many people don't really know the limitations, and they think it's a 3D printer. It can print everything. Yes, it's possible to print everything, but some things are way faster to print than other things.
Thank you.
Thank you.
Now, we started with a genome. We went up to an organism, then a plate of masa. Now this size. Now we're going to have, we're fortunate to have Sally here joining us to talk about really big things.
This is the ShopBot headquarters in Durham, North Carolina, and I know that there are a lot of ShopBots out in the world, and people tend to think that we are this huge company, but really we're a small factory with about 30 employees, and we use another. It's okay, it doesn't need to be powered. That's fine. So we also employ another couple of factories locally, but everything but our motors and the extruded aluminum is made in Durham, North Carolina. ShopBot started because Ted Hall, who was on the faculty at Duke University in the psychology department, wanted to build boats. And he wanted to build a hard chine boat that had very precise cuts because you were taking flat panels and bending them and stitch and gluing them together. And if you made a mistake in the way that you cut it, either the panels wouldn't fit together or you would have a hole that water leaked in. So at the time, he was looking for CNC machines, and the cheapest one he could find was a $40,000 used CNC machine. And he didn't think his wife would let him buy it. He never asked me, but he decided what he would do is he would build his own. The first ShopBot was built with parts from the local do-it-yourself store, the Home Depot. So it was built out of 2x4s, strut, and rollers from screen doors. It was a great invention, but it didn't hold its position very well, so there was a lot of warping. It wasn't very reliable. There have been a number of versions of the ShopBot. These are the most recent ShopBots. The desktop, which is extruded aluminum and steel, is under $7,000 with a spindle. The 5-axis tool is under $40,000. ShopBot is very interested in education and innovation, so we work with schools. We're delighted to be associated with the Fab Labs all over the world, including some of the pictures are from our week here at the Fab Lab in Lima. Some of the things that we like to do are to have people build things with their ShopBot, such as the linker logs, if you look on the bottom. That those were built with a ShopBot, and then children can use their imagination to build things. So instead of it just being digital fabrication that you're on a computer, that you're actually physically building and getting the feel of things and learning what the dimensions of the shape are. So in a school situation, the older children could be using their ShopBot to make the linker logs that then the younger children could use. And they, all of the angles have the degrees of the angles written on the logs, so they're actually learning geometry through hands-on representation rather than just trying to graph it out or learning it from a book. And it's really been amazing to watch kids use their imagination and learn to play with this. There are many, many applications for a ShopBot. So this is an artist who's in the Midwest. He uses his ShopBot to draw. These particular drawings are both black ink and then white ink. The same artist uses his ShopBot to make plates for printing. So he does large-scale printing on Japanese paper. And the darker the image, the more number of layers on the print. So he will do an image like this would take 12 to 15 layers, each one that has been carved in plywood on his ShopBot. Another artist created this at a Fab Lab in New York. Sorry that it goes off the screen, but he's actually using his ShopBot to mill aluminum. And then he used other features of the Fab Lab to put LEDs and predict the weather. This was a feature that was up in New York for about 6 months. ShopBots can be used as molds for casting. So this was a mold. The original artwork was just a PDF that was delivered, then brought through. Then MDF made the original that was a positive, similar to what the mold would look like, cast in resin and sand, and then the bronze was cast into that. And we have 3D carving. This is a traditional woodworker who decided he would try to see what a ShopBot would do for him. Theater design. In a 2-week period of time, this set had to be created for a play that was at Duke University. So I used the ShopBot and created 90 panels, and each panel had between 350 and 450 plunges. So we ran it for 8 hours a day, but we got all the panels done. ShopBot is also used in manufacturing, and it's really involving a different way of thinking about manufacturing. Traditionally, a manufacturing company would buy one CNC machine. It might be a $250,000 to $1 million machine. Everything would go into that workflow and then come out, and if that machine was down, then the company was down. In a distributed array CNC, a company might take several smaller CNC machines that they are using to make individual parts. So it might be a part for boring, it might be a part for creating rails and door frames. And the parts can be moved, the CNC can be moved around the factory as it is necessary. So on the top, here's a picture of Woodmode. It is a factory in the Midwest that does about $4 million of sales in cabinet doors a week. And they have 24 ShopBots that they are using. They started off with buying their first ShopBot in 1999, and they were going to use it to make templates so that they could then use hand routers to cut out the parts. Then they realized that they could take the ShopBot and use the ShopBot to cut out the parts, and they threw away 400 templates. They also made bushings so that they could do the drill patterns for every time they changed the hole drilling in the hardware. And then they discovered that they could use the ShopBot and create a new pattern and do the drilling with the ShopBot. They threw away 40,000 bushings, and they run 8 ShopBot programs at this point. A lot of people have small businesses, small scale manufacturing, so it could be a sign maker, it could be a boat builder. They are using ShopBots as the basis of their business. And of course, in sign making, it is definitely the finish work that makes the sign, but the ShopBot makes that part of it a lot easier. There's also individual people have ShopBots, or if you want to do contract cutting, so you have a design that you would like someone to cut for you, there is a network of ShopBot owners called 100K Garages. They are local, so you can go to 100K Garages, contact someone, see whether they can manufacture your device for you. There's also Pinoko, based in New Zealand, but they are looking for local manufacturers so that you could send your design to someone and have them manufactured locally. In this example here of the sketch chair, it was a company that was started in Kickstarter. It's a fundraising organization that you put it up on the web. You say you need a certain amount of money. People donate to your fund. When you reach your level, you get all of the money. If you don't reach your level, you get none of the money. But usually there's some sort of little manufacturing, little device, little gift that they're giving for your level of of donation. And so this is the sketch chair. It is currently funded, and so the prizes are being manufactured in Virginia and being sent out. The idea of sketch chair is if you have an idea for a chair, you can send it to the program, and then you can look at the physics. Let somebody sit on the chair or a model sit on the chair, and if it's going to fall over, then what are the changes that you need to make in order for that chair to work properly? One of the people at ShopBot is a new employee. He's been there since January. He worked in a technology high school where they did everything by hand. And he has come to ShopBot and turned a lot of his handmade objects into digital fabricated objects. So he has a project that they did for his school that took 90 hours to make the chairs. He can now make each chair in about 20 minutes. This is the owner of ShopBot, Ted Hall. One of the things that we've always been interested in is making the software extremely easy for people to use. We've been through various software companies, and we're working now with a company named Vectric, which is it's a very fun company to work with. They've made their software very easy to use, and they have just done a project with taking a K'NEX game playing system and using it to do 3D modeling, and this was cut out in about 20 minutes. So, what are some of the big projects that Fab Lab has done? I'm sure you've all heard, because this is a Fab Lab, the Fab Lab in Barcelona, done through the EOC. The outer structure was actually created by a CNC company in Germany, but the smaller pieces, the whole inside, was created on a ShopBot, cut out in a matter of weeks and assembled in Barcelona, disassembled, and then taken to Madrid for the final show. This is Larry Sass from MIT, and they did a series of 5 houses that they displayed at MoMA, the Museum of Modern Art in New York. And this is the Katrina house. The idea of this house is the entire house is fabricated from parts that slide together. So there's no hardware. Everything is put together with a mallet. It took them about 2 weeks, no, I guess about 7 days to put it together. All of the parts were again manufactured in Virginia, put on a truck, and taken up to MoMA. This is the Burning Man. It's a festival that takes place every year in the south of the United States and is apparently quite a wild festival. They build a huge structure and then they burn it down. Bill Young, who has worked with Shopbot since the very beginning. In fact, he was one of the first owners of a Shopbot, maybe Shopbot 3, and he traded the Shopbot for a boat. So finally, Ted got a boat, but he didn't build it himself. He and Bob Bridges are working with using structure that they actually take plywood, and they do a joint, if you look in the upper left-hand corner, that they are taking a joint and they are putting pieces of plywood together in such a way that it becomes thick enough to become timber frames, and then it can be used in manufacturing, for manufacturing houses. Bob Bridges also is using his Shopbot. He has a company called Shelter 2.0. One of these structures can be shipped to Haiti or another place that has had a disaster and so needs housing. And the whole thing can be put together in about 20 hours with just a few bolts and with entirely unskilled labor. This one has corrugated tin on it. It could also have, corrugated isn't the right word, but anyway, it has tin on it. It can be also used with just a plastic shelter if you need it. This is Bob Bell, who actually worked with Lego as a designer. This is also the bottom picture at Burning Man. And he's very interested in taking geometric shapes and figuring how to carve them with the Shopbot and assemble them in a way that is not your traditional square housing. This is another house, a couple houses, a little dog house and a playhouse were assembled at either the San Mateo, California Makers Fair or the Austin Fair. Again, these houses go together with no hardware. It's just putting everything together with a mallet. And a little bit more organic. In this one, you can see the parts, the way that they're laid out on the Shopbot, and then the way that they are all assembled and put together. And Bill sent along some things to do if you're creating a large project like that, which is basically keep track, make sure that you label everything, keep a record of what you're cutting so that you don't cut everything again. Don't take all your parts out. Keep everything tabbed in your sheet until you get to your final location, and then wait until you take it out. And this is available. This will be available if you need it. And that's it. Okay.
Questions, comments about Shopbots and big things? And then somebody will translate.
What is the precision and the importance for fabricating with the Shopbot? So you're asking about the precision of the Shopbot? For a big piece? Well, anytime you are using a Shopbot, do you want to come in?
Or just somebody in the audience? All right. Yeah, we don't need the speaker, just a Spanish speaker to translate.
If I'm here, the translators can translate. So the question is, what is the precision, and what is the precision necessary for fabricating these large structures? Yes. Okay. The precision of a well-tuned Shopbot is 0.002. So, and that's in inches. So it's much greater. Think about it in millimeters. And I can't do the translation in my head. Anyway, the Shopbot itself. 50 microns, okay. So if your ShotBot is tuned, and you can make them as precise, and you can actually do some test cutting, because the problem is not the ShotBot itself. The problem is the plywood, the Madera that you are using, that it can vary. So if you are sliding pieces together, you need to do some tests to make sure that your slot is the appropriate slot. But it's not a problem with the ShotBot in terms of cutting it.
The question is very important because the ability to make those beautiful structures rests on control over a few thousandths of an inch. If you're off by a few thousandths of an inch, it either doesn't fit or falls apart. So the precision is really the matter.
You need to speak in here if you would like them to translate. Okay.
Say it again. Thermic?
What are the thermic qualities of the product? How it function when inside houses? How does the product heat, or what are the characteristics of the product in thermic terms?
Are you asking what you can cut with a ShotBot? Or can you have a ShotBot inside your house? I have one in my barn.
I was asking about the characteristics of the material inside. Does you feel warm inside, or do you feel cold? How the transmission of the heat?
No. My ShotBot is in my barn. I am in North Carolina. In the winter, it can be Fahrenheit 17 degrees, which would be minus 6 degrees Celsius. I wear lots of clothes. In the summer, maybe 30 degrees Celsius. So the ShotBot itself can stand a wide temperature range. The materials, if you're working with wood, if you're working with plastic, if you're working with aluminum, they are going to be affected by the temperature. But the ShotBot itself is not. Does that answer your question? Good.
Okay. Okay, thank you, Sally. And the lesson from that is you really can do rapid prototyping on the scale of housing now. The range of the scale keeps growing. So the last presentation, we're fortunate to have Chris Anderson joining us. Chris is known, while I do this. Chris is known to many people as the editor of Wired, but I think he's known more to his kids as making cool things fly. And that's been quite a journey. So I'm now going to unmute Chris's audio, and I'm going to mute our audio and wait a moment while we make sure that the computers are connected.
Hi there, can you hear me? I guess you'd have to nod or wave.
Sorry. We hear you fine.
Oh, okay. So I guess I'll just say next slide, and then people will be able to advance the slides on that side. So I'll get started. Neil, thank you for inviting me to this. I've been to a few of the Fab Labs. They're always inspirational. Your book has inspired me hugely, and I feel like I'm the maker I am today because of your example. So I'm privileged to be here, and I'm delighted that this is happening in Lima. I'm going to give you a little sort of overview of what I think it is that we're doing here from kind of almost an economic perspective, and tell you a little bit of my own story, my own experience as a maker and as somebody who's using these tools to build a business. I've been describing this as a new industrial revolution because it has the same ability, I think, ultimately, to create a different form of industrial economy than the last industrial revolution. Could I have the next slide, please? And this is my thesis, really, just in a nutshell, that the last few decades on the web, we're finding a new way to work together in the open, as communities, collectively contributing to something which was digital. The next few decades are going to be to apply that innovation model to the real world, to physical things, which is a much bigger market, a much more interesting opportunity. And I think that the web was just the prototype for what is ultimately potentially the industrial structure of the 21st century. Next slide. The first industrial revolution was largely about a centralized infrastructure, which is to say that we operated around the factory. The people came to the tools of production, which were largely driven by big machines, first water, then steam, then electricity, and then beyond. And it was a very clumpy experience. You had big factories that defined cities, that owned the tools of production, and they only operated at a massive scale. You could only make the things that worked on a mass market. Next slide. The next industrial revolution, if you will, is the information age. And that one was notable for its two steps. The first is that we democratized the tools of prototyping. And that was that, what you see there on the left is the laser printer, the first laser printer, the Apple LaserJet from 1986. And that led to desktop prototyping tools, which are, as you know, incredibly powerful and liberating, but they could only make a few of something. That democratized the tools of prototyping, the tools of making a few, but didn't democratize the tools of making many of production. That required the web, and in a sense, the blog and all the other things we now know today in social media and beyond are basically printing presses for mass scale that are impedance matched to the individual, which is to say that anybody can publish globally with a click, and therefore the tools of distribution are now as democratized as the tools of creation. And there we have a full end-to-end, industrial model. Anybody can make anything and get it out to anybody anywhere else. Now that parallel, production distribution model, next slide please, is playing out in the physical world now. The MakerBots, and that's what I happen to be using as a demonstration in my basement, but there are many other CNC machines that we just heard about, laser cutters, CNC quilters, sewing machines, all that stuff. Those are all the equivalent of the laser printer, which is to say they're democratized prototyping tools. They allow us to make one or two of something brilliantly well, and that's really important. So what is the equivalent of the blog then for physical goods? And the answer is that it is these web-based service bureaus that basically allow individuals to get huge factories to work for them. I've shown you here a slide of Alibaba, which is a web-based interface to Chinese manufacturing by and large. And what's fascinating about what the changes in Chinese manufacturing over the last few years has been that they've gone from really only operating at a mass scale for commercial customers to operating at any scale, including for individuals. So, what's transformative about this generation of makers, as opposed to the tinkerers of the past, is that everyone's operating with digital files. You create an object on a screen, you can print local on your desktop device, or you can print global by uploading that same file to the service bureau, which will make any number you want. And so the file format compatibility between the one and the many, between the desktop and the factory, is the really unique factor in this new era. And not only do these Chinese factories use the same file formats that you use on your desktop tools, but they will accept orders of as few as 1, 10, hundreds, small numbers of thousands. They'll take credit cards, they take PayPal. They're willing to work with individuals. You don't need a letter of credit. You don't need to fly to China to have a face-to-face contact. They're very web-based, companies now, and they've done that for a number of reasons. First, they did it because a generation of web natives came into management. It just took that long, but now the people who run Chinese factories today are web natives. They get it. Second of all, in the recession, they were looking for new business, and they realized that selling small batch custom products could get higher margins than the commoditized large volume products they were making for big customers. And thirdly, their tooling is now digital. So that means they can create, they can adjust their machines to make a new product very easily, which allows them to do these small batches without incredibly big costs. So those structural changes on the factory side have allowed anybody to make anything and get it to a global audience at any number, at any volume that makes sense. They can even drop ship it directly from the factory to the customer, and you don't have to take receipt. Next slide, please. This is a picture of my grandfather. His name was Fred Hauser. He was a Swiss immigrant into the United States, Los Angeles, in the 1920s. He worked in the film industry at MGM. He was an engineer. The film industry was a very mechanical business in those days, involving tape drives and things like that. But he was an inventor as well. And this is him at home on his workbench, where he was using, he was drawing cool things. Next slide, please. This is what he invented. He was the inventor of the automatic sprinkler system, and had a patent on that, and our very small family fortune came from the automatic sprinkler system, which was exactly, if you took a Swiss watchmaker and put them in Los Angeles, that's exactly what they would invent. A sprinkler system is basically an irrigation system with a clock on it, a timer on it, that would automatically turn on valves and things like that. And those are the valves and the solenoids that were automatically being turned on. It's the clockwork lawn, if you will. Next slide, please. This is the patent. Next slide. This is me as a child working with my grandfather in his workshop, learning how to, we were learning how to use metal lathes and things like that. It was really inspirational. Next slide. That's me actually learning how to do mechanical drawing. That's me learning how to use the metal lathe as a 12-year-old in the workshop with my grandfather. And, I loved my summers with my grandfather in the workshop making things. But in the end, I didn't follow this path. I didn't go straight into engineering and become an inventor. And the reason I didn't is because I couldn't see, because he was an inventor, but he wasn't an entrepreneur. I wanted to be an entrepreneur. I wanted to run businesses. And my grandfather was always a solo operator, operating by himself in his workshop. Other companies made those products. He had to license his patent to a big company and lost control of it. He did fine financially, but he lost control. And that wasn't interesting to me. Next slide, please. There's a film called Flash of Genius about the invention of the automatic, the intermittent windshield wiper, which I won't go into, but it's the same story. Inventor in the basement does something awesome, patents it. In this case, this inventor made a mistake, which is that he decided he was going to make it himself. He was going to go into production, and ended up bankrupting himself trying to build a factory, and his patent and his idea was stolen, and he was driven crazy. That old model, I think, is what was a barrier to entry for many inventors. You could invent something, but you couldn't get to market. I think the new tools allow us to make things ourselves, to go into production ourselves, to become entrepreneurs, not just inventors. This is an example from Tech Shop. Next slide, thank you. This is an example from, next slide. This is a Tech Shop, which is like a Fab Lab, but a commercial one. Those are all entrepreneurs who are not only making prototypes, but also uploading those files to factories to make large numbers. Had my grandfather been alive today, that's where he'd be working. He would be an entrepreneur, not just an inventor. Next slide, please. This is just the spread of hackerspaces around the world, and things like Tech Shop and Fab Labs are all examples of what we call makerspaces or hackerspaces. They're booming, and fundamentally every city should have one. The model is like the gym, where you become a member in a gym, and you share expensive equipment that you couldn't afford by yourself. You have trainers who help you. You work with other people who are trying to get this positive reinforcement. The gym model applying to making is really taking off. Next slide. Next slide, please. So this is the sort of the model that you have, this distributed manufacturing model and these open innovation models. And together, what we're going to create is a new class of product, what I call the long tail of things. And what that means is that these are going to be niche and unique products that don't fit the traditional mass manufacturing model of production, that won't go on those shelves of Walmart, that won't be manufactured in the tens of millions, but that do find niche niche audiences on a global basis. The 10,000 model is a perfect example. There's a lot of products that would find a global audience of 10,000 that don't fit the existing production systems. And this combination of open innovation that makes it possible to invent these products faster, cheaper, better, and distributed manufacturing, which allows you to do it without owning a factory, allows us to finally scale down from the millions to the tens of thousands and tap this new sector of demand of niche and unique products. Next slide, please. My own thing is I do drones, and I got into this basically with my children a few years ago. They quickly realized that the Moore's law of sensors and the fact that in every phone you have gyroscopes and accelerometers and GPS and wireless and all that kind of stuff necessary meant that you could create an autopilot very cheaply and basically turn any vehicle into an autonomous vehicle by just adding a box. Those boxes cost tens of thousands or hundreds of thousands of dollars when they're made by aerospace companies. We thought that we could take 2 orders of magnitude out of that cost, maybe 3, by doing open source using commodity sensors, and that's what we've done. Next slide, please. This is what we make. It's an Arduino-based open source autopilot. You can do airplanes, helicopters, quadcopters, multicopters of all sorts, cars, boats, blimps, everything. It's a universal autopilot. It costs $250. Next year it will cost $150. This is basically benchmarking against military autopilots that cost hundreds of thousands of dollars. It's open source. It's created by a community. We now make more. We put them in vehicles, and we sell more drones than Lockheed Martin. Ours are not as good as theirs. Ours are a lot cheaper. Ours are not made for military purposes. But the point is that a community of amateurs, including students, can collectively reinvent the aerospace industry from the bottoms up. Next slide, please. This is one of the kind of things we do. This is one of our quadcopters, and it's a robot. It's fully autonomous. The amateurs in this case are well ahead of the professionals in creating this kind of flying robot. It's an example of how the web model really can apply in high technology of physical goods. Next slide. Our model again was to look at this. We looked at the existing marketplace of UAVs or drones. UAV is unmanned aerial vehicle, and we saw this sort of order of magnitude progression. For the $10 million products sold in the single-digit numbers, the $1 million products sold in the tens, etc. And that was kind of the whole drone market. And we decided, well, what about everything else? Next slide, please, or rather, click forward. Click, please. Yeah, you can just click through all the animations here. Basically, we decided to start at $1,000 and target 10,000 of these. But the next step will be $100, and we'll go for 100,000. And then ultimately, the whole technology is going to be a chip, and it's going to be this kind of autonomy chip that you can add to anything. To make it autonomous is where we intend to go. There's no way the aerospace industry is getting here. They think in terms of $1 million contracts and absolute 100% reliability, no failures. They treat robots like manned aircraft, and that they have to be perfect. We treat robots like disposable meals ready to eat. We send 10 out and 8 come back, and that's okay because they're so cheap. And if you consider them as disposable, you double the range because they don't have to come back. So we come at this in an entirely different approach. We think of quick, dirty, simple, cheap, using commodity products. Ultimately, these are going to be made by toy companies, not aerospace companies. We see this as being a radically different model. And in the process of going this way, doing the bottoms up rather than the top down, we hope to not just do drones, but also avionics and aerospace, ultimately vehicles of other sorts, including cars. We see this as an extremely disruptive model of open source hardware applied to traditional industries. Next slide, please. So this is basically just a kind of a map. I don't have time to walk through this, but you'll have access to these slides. This is just a map of all the things that are different about hardware and software. Basically, software is a lot more complicated. Hardware is a lot more complicated. There's many more layers and steps, and there's a lot of questions we have about licensing and the right organizational framework. But I don't have time to walk through this, but it's there if you want more. Neil? Speaking of which, 2 minutes. I have 2 minutes?
Yep.
Sorry?
2 minutes.
2 minutes to finish or 2 minutes on the slide?
2 minutes to finish and then questions.
2 minutes to finish and then questions. Okay, I'll zip through the rest. Next slide, please. So this is our business model. Basically, we give away the bits and we sell the atoms. Our margin is transparent to the public. It's 2.6 times the cost of the goods. That allows for 2 40% margins, one for us and one for our retail partners. So we sell wholesale at 40% margins, and then our retail partners put on another 40% margin. 2.6 times the bill of materials cost means that it can be very, very cheap. Most companies charge something like 26 or 260 times the bill of materials, but we don't charge for intellectual property. It's all the software, all the IP is developed by a community. So it's free for us. It's very fast, very cheap. Next slide, please. I'll just zip over this very quickly. The hardware is made by a traditional company. Where we have a factory in San Diego. We have employees. We pay them well. They work 9 to 5. The software is created by a community of volunteers, and the software brings the hardware is simply commodity hardware. But it's very important that we do that we make it ourselves, and that we support it, and that we work really hard on quality control and keeping our inventory up so that it never goes out of stock. But all the value comes from the software. Which is created by a community, is constantly changing. So, you buy a product from us, and it gets better every day as the software improves, rather than getting worse. It's the opposite of planned obsolescence. This is planned improvement. Because it's open, the community is highly incentivized to make it better every day, and to continue to extract more value out of the same hardware. Next slide, please. This is if you can just click through all the elements here on the slide. This just tells us how we compensate our community members. Basically, the first time you commit, you get like a T-shirt. Then over time, as you can contribute more, you get hardware discounts. Then you get free hardware. Then you get a trip, expenses paid trip to our dev meetings. Then finally, for the team leaders on major shipping projects, they get equity in the company. So this is how we align our community's economic interests with our own. People don't want us to pay them a royalty, because it would only increase the cost of the product. And fundamentally, they're doing this not for the pennies they would make from the royalties, but to get a product out to more people. So the lower the cost of the product, the more the sales. The more they get out there. So they want to keep the product as cheap as possible, but if something becomes incredibly successful, they want to have a stake in that as well. So we think that the equity model, which we pioneered, I'm not sure anyone else has ever done this, the notion of giving equity in a company to open source contributors, we think this is ultimately going to be a good way to ensure that we're compensating the right people for their contributions and recognizing the work in the product. Next slide, please. The question is, people think a lot about where should things be made. Is it all about outsourcing to China, or should we bring it back? And basically, it moves back and forth. We start with making things locally, prototypes locally. The first 100 we might outsource because we don't want to tool up for that. The next, once we get to the next 1,000, we tend to bring it back, because at this point, quality control is really important to us. Inventory management, being able to iterate the products very very quickly. So flexibility is really important at the scale of thousands. And once we get to tens of thousands and beyond, at that point it's beyond our own manufacturing ability, and we send it back to China at that point. But then we don't iterate it and change it that often. At that point, it's a relatively fixed product. Next slide.
Chris, we have to get to questions.
Okay, I'll make this the last slide. Only I just want to point out that this is that our model, which is started by amateurs, is now the model for the U.S. government. And the DARPA, the Defense Advanced Research Project Agency, the research arm of the Pentagon, has adopted our open source innovation model for the future of military UAVs as well. This is UAV Forge, which they modeled after DIY drones. And the point is only that they're listening, and they see they want to try it out on a government and mass scale as well. Thanks, Neil. I'll take questions now.
questions for Chris about flying drones, business platforms, about industrial revolution, about lawn sprinklers, or about lawn sprinklers.
The first thing that you said about the analogy of
Chris, I'll repeat. Yeah, no, go ahead.
The analogy of logs and distribution. So if you have a laser printer, you have a printing press in your home, and logs allow for distribution. And your analogy was that if you have manufacturing that you can do at home, that's the equivalent of a laser printer, and your distributive analogy was to send the files to China. Is that correct?
Can you turn that into a question?
The question is basically how.
Sorry, Chris, if you can see the mute, that would be helpful.
Sorry. How is distributed manufacturing in China the future when people have manufacturing in their homes?
Chris, the question is relate distributed manufacturing and send to China.
How's that a question?
The question is,
there's the distributed manufacturing model, and there's the send to China model. You talked about both. How does distributed manufacturing relate to send to China manufacturing?
So distributed is a scale question. I think I'd go back to that one that was sort of the sine wave. The point is exactly that one. Thank you. The point is that you can choose whether to move in China or do it locally depending on the scale. The old model was that you only had one choice. You had to tool up and have some big factory make stuff. Now you can choose whether you want to make it locally or globally, depending on the scale and your own needs. So what distributed manufacturing does is allows you to get started with a relatively low volume rate to test the markets, and that's the first part, the left hand side of that curve. You're doing that with local tools, possibly prototyping tools. You're making hundreds, and you could use that to beta test the product and test the marketplace. Then you can then scale up very quickly by going to China, because they'll now work with the relatively small scale people in the way they wouldn't before. And then finally, once you've got that, you realize you're now a real business. Now you can bring it back locally again to maintain quality control and have flexibility in the manufacturing, because those same tools are cheaper and available to you as a small business in a way that they weren't just a few decades ago, because they're all digital and they use the same formats at all scales. And so that sort of digital file scale agnosticism of the new digital manufacturing chain means that you can either be local or global depending on the size of your batch.
Okay, and that's a softball question for the session after lunch that's going to talk about business platforms, because there's interesting hybrids. Let's do one final question before lunch from a new part of the audience. I'll repeat it. Go ahead.
Hi, Chris. What do you think is needed to move from to make your hardware open source and get, for example, distributed manufacturing from your products, let's say in a Fab community, not in a single factory in China, but to distribute that.
For time, I'm going to pause on that question because we have a whole session on business platforms. So let me ask you to leave that question hanging, and we're going to pick that up in the business platform session. For time, allow me to do that, and let's focus on things specific to this session. One last question. Did you ask one before? Yeah, no, you only get, to be fair, let somebody who didn't ask the question ask one.
What?
You already asked a question. I want to be fair to let people who haven't had a chance ask the question. Okay? Sorry. I'll introduce you to Chris later, but let's take somebody new over here who hasn't had a question.
It seems that the democratization of technology allows the technology to fall in the wrong hands. How do you prevent that?
Okay, so Chris, question is, drones can use to blow people up. Comment.
Yeah, I get that a lot. Yeah, that's true for all technologies. All technologies can be used for good and for evil. We do our best to promote positive use. We don't allow any discussion of military or weaponized use. The point is that these technologies are too important to be left to the military. They should be put in the hands of individuals to be used for aerial surveys, scientific sensing, crop management, all sorts of, fantastic civilian uses which are not affordable or allowed because the technology is controlled by the military-industrial complex at the moment. It's actually a really poor technology for weaponization. If you want to ship a bomb to something, you can use FedEx. You can use radio control airplanes, which are not autonomous, much cheaper, much easier. We're not making chemical warfare agents here. We're not making biological warfare agents. These are not weapons. What they are just robots that have, we think, a huge application in the civilian sector, but they've been too expensive, too hard, too controlled to really try. So think of this as a mainframe versus personal computer. Right? Once upon a time, only people who had mainframes could use computing. Then the personal computer came out, and we could all figure out what it was for. Some people used it for good, and most people used it for good. Some people used it for ill. But it's the same process. We need to put technology in the hands of everybody, so that they can figure out how to use it best. And we hope that most people use it for good, but we can't do anything to stop them from using it for ill.
Yeah. My favorite answer to that is blowing people up is a mature market need. I'm sure a few blocks from here we can get all sorts of ways to hurt people. These are tools to do other things that are less well-met market needs or new opportunities. We're really out of time. Anybody who didn't get to ask a question, come find me and I'll introduce you to Chris afterwards. And I apologize, but we need to stay on schedule to respect the speakers throughout the day. So with that, let's thank Chris.